Hello, everyone. My name is Masqueram, and in this video, we're going to talk about how to find output noise of an analog or an RF circuit. So let's look at the topic for this video. First of all, we're going to discuss the motivation for finding output noise in a circuit. Now, to some of you, this might be very obvious, but if there's any beginners in analog IC design, this may not be as obvious. Like, what are we trying to achieve by finding the output noise? And so we'll go over the motivation a little bit, and then we'll talk about the procedure to find the output noise, which is just a bunch of steps that we follow, and then to show you, how to execute those steps to find the output noise, we will do 3 examples. All right. So before we start, I want you to recall 2 things from previous videos. First is the thermal noise in a resistor, and the mean squared current value for that is 4 kdB over R, where K is the Boltzmann constant, T is the temperature in Kelvin, B is the bandwidth, and R is obviously the resistor value. And then also the thermal drain noise of a MOSFET is IDN squared, IDN mean squared. That's how I represent it in this video. And it's equal to 4 kdB GM gamma. And which GM? This is GM of the transistor, okay? And gamma is just a constant, which is 2/3. All right, so let's get started. Let's look at some of the motivation for output noise. And here, I want you to imagine this circuit. It's 5 transistors, M0, M1, M2, M3, and M4. Let's say this is the output node, and this is Vin plus, and this node is Vin minus. By the way, this topology is also called the 5 transistor OTA, and it's a pretty common, first stage in a 2-stage amplifier. Or you can even use this stage as an amplifier itself, depending the application and your needs. But let's say this would be Vn plus, and this would be Vn minus, and this output node is the same as this output node. Okay, so let's say I want to know what the noise at the output, which is this node, looks like. Right, I'm interested in that, and so this is the same as the noise at this node. Right, so that's what I'm interested in. Now, in the previous videos, we said, we talked about how MOSFETs exhibit thermal drain noise, and some of that noise also gets coupled to the gate. We talked about the flicker noise, we talked about shot noise, and all the the noise discussion. But let's say I ask you this: M1 has the drain has like thermal drain noise. So how does that noise contribute to the output node of my amplifier? I could ask the same question for M2. M2 also has thermal drain noise, right? So how does that noise contribute to the output? How much of that noise shows up at the output node of the amplifier? And so you can see the line of questioning I have over here, right? I can also ask the same thing about M3. How much noise does M3 contribute to the output? How much noise does M4 contribute to the output? I could also ask this: which of these 2 transistors, M3 or M4, contribute a higher noise to the output? How much noise does M0 contribute to the output? And so you can see, like, or I could also ask this: given this 5 transistor topology, if I want to make my op amp as low noise as possible, which transistors should I focus on the most? And what design parameters should I change for that transistor to reduce the noise? So that's the kind of things that we're trying to think through, and we're trying to answer. And so what we will do is look at each, whenever we have a schematic, we will look at each one of the components, transistors, resistors, and we will see how much noise do they contribute at the output of the circuit. And then we will derive expressions of the noise contribution at the output from each component in the schematic. And then we can discuss like, which component in the schematic contributes the highest noise, and we can see why, right? And we can also see the design parameters through those expressions. We can also see the design parameters that need to be adjusted to achieve the lowest possible noise, or to reduce noise relatively. So that's the motivation, right? And the method that I just mentioned over here, individual noise sources in each transistor, and how they contribute to the output noise. This method is usually used for analog and RF circuits as well. In fact, in Cadence, you can also, there's a way to do the simulation, and it will tell you each component in your schematic and how much noise it contributes to the output. So that is possible, and you can search other YouTube videos to see how to do that sort of simulation. And so, but my point is that noise analysis can be done in different ways. So this is just one of the ways. But for example, in Mimics, they have sort of a different way to analyze noise. They would do something like source pulling, and they would figure out the optimal impedance that gives them the best noise figure. And the tools might be also different. They could use like ADS or AWR for their analysis. So again, we're trying to get to the same thing, trying to find like the point where, or the region where you would get lowest noise. But the ways of doing noise analysis might be different depending on the kind of circuits you're looking at. And for the purposes of this video, though, we are looking at the method for analog and RF circuits. Okay. So let's look at the procedure or the steps to find the output noise of any given circuit. We can start with shorting the DC voltage sources and open the current sources. And then we can also short any small signal voltage sources and open any small signal current sources. Then we can draw the small signal model, and we can insert the noise source. It could be a voltage noise source, it could be a current noise source, and it could be modeling whatever noise you want. It could be the drain noise, it could be the gate noise of a MOSFET, it could be the resistor thermal noise, it could be all three of them being analyzed at the same time, or it could be a combination. It could be just two of them. Let's say only the thermal drain noise of a MOSFET and the resistor thermal noise. You could only consider those two and not model the gate noise, right? So it just depends on your application and what kind of noise is important to you. Typically, when you model more noise sources, your analysis becomes much more complex, lengthy, and time-consuming, but also more accurate. On the other hand, you could reduce the number of noise sources that you're modeling. That will simplify your analysis, make it quicker, more intuitive even, but at the expense of lower accuracy. So typically when you're designing, it's sort of a trade-off, and you have to, as a designer, you're trying to strike the right balance between complexity and simplicity. You're trying to strike the right balance between the time consumption of the analysis versus the accuracy of the analysis. All right, so after you do these 4 steps, the last step is to solve for the output noise. All right, and by the way, these steps in blue, they don't have to be in this particular order. The point is to just execute all these 4 steps before you solve for the output noise. So that's how you can interpret this procedure. All right, so let's look at some examples to see how we can follow these steps that we just talked about and find the output noise. So example 1 here, we have to find the output noise, which is the mean squared output noise voltage of a common source amplifier. Now, in this example, we have to model only the thermal drain noise of transistor N1. Okay, so let's look at the steps again. The first step was short any DC voltage sources and open any current sources. So we have DC voltage sources here, V bias and VDD. So we short them out. Then we can short out any small signal voltage or current sources, voltage sources. So we have a small signal voltage source over here. We could short that out. And then we can draw the small signal model. which I have over here. All right. And then fourth step is to insert a noise source, with whichever noise source. So in this example, we're told to, um, you know, model the thermal drain noise. So we'll do that. That's the thermal drain noise, again. Okay. And then we can solve for output noise. So let's start writing down the equations. First, we can do KCL at node V out and sorry. So this is the node we're trying to look at and find the output noise at this node, right? So let's look at some equations. So this would be GM1 VGS1 plus VL10 GS1 plus IDN, which is the thermal drain noise, and V out N GL equals 0. Oh, by the way, GL is just like RL, but represented in conductance instead of resistance. So same thing, just makes conductances make our KCLs easier to manage. All right, so VGS, you can notice, is 0, so we can ignore this term, and then I can simplify a little bit. I can write, we have GDS1 plus GL plus IDN equals 0, and I can simplify it more and make V out N as the subject of my equation, and then I can write minus IDN over GDS plus GL. All right, so that's the output noise voltage, but remember, we're trying to look for the mean squared output noise voltage, right? So we can take the mean square of this expression, V out N, mean squared, and so here it would mean multiplying IDN with its conjugate. So it should be this, all right, and so that, and in the denominator, it's just a square. All right, so now IDN multiplied by its by its conjugate, sorry, is the same as if I multiply IDN with its conjugate, it's basically IDN mean squared. So this would be V out N squared, V out N mean squared, and at the top you would have IDN mean squared, and at the bottom you would have GDS1 plus GL squared. And then we can also substitute in an expression for IDN, which is the thermal drain noise. So I can write it, I can simplify it a bit more and say IDN mean squared. We said that this is the expression for it from the previous videos. So we can say IDN is 4 kdB GM gamma, and then the denominator remains the same, GDS1 plus GL squared. Now, important to note here is this GM, which GM is this? It's GM1 of this M1 transistor over here, all right? So just something to note over here. So that's the final expression for output voltage noise of a common source amplifier. So let me write it down, output noise due to thermal drain noise of M1. So that, remember, that's the only noise source that we have modeled right now. it's just the thermal drain noise of M1. Okay, so that's the output noise contribution due to the thermal drain noise of M1. All right, let's move on to example 2. Here we have to find the output noise of again a common source amplifier. The only difference though is this time we're modeling the thermal noise of the load resistor RL. So again, same thing. We short out these voltage sources, V in, V bias, VDD, and then we draw the small signal model, and then we can add the noise source. In this case, it's the thermal noise of the resistor RL, and it's represented by IRN. And then the exact same procedure as we did in example 1, we do a KCL and then we write an equation, and within 2 or 3 steps, you will come to this final expression, which is output noise due to the resistor RL. Okay. And now let's look at example 3. So find the output noise. Sorry, this shouldn't say input preferred noise. It's just find the output noise of the common source amplifier. So same circuit, but this time we're asked to model both the thermal noise of the resistor and the thermal drain noise of the transistor M1. So both the noise of this and the noise of M1, and see the total output noise contribution at because of these two components. Now, let me, again, same steps. We ignore, or we short out V in, V bias, VDD, and then we draw the small signal model over here, and then we can insert the noise sources, which is the one due to the resistor, and the thermal drain noise due to the transistor M1. Call it IDN. All right. So let's before we dive into the math, let's think about this a little bit. In example 1, I asked for the output noise contribution due to the thermal drain noise of M1. In example 2, I asked for the output noise contribution due to the thermal noise of resistor, right? In example 3, I'm asking for both of them at the same time. So the question is, do we have to rederive, for the output noise contribution from both of these sources when we have done the same analysis for the noise sources individually? The answer is no, right? We can use our derivation from example 1 and example 2 to find the total output noise contribution due to both the circuit elements, the resistor and the transistor. So yeah, that's exactly what I've written here. Do we need to rederive? No. We can use our derivation from example 1 and example 2, and then we can use superposition. So let's look at that. So V out N total. So this is the total output noise due to both the components, the load resistor and the transistor M1. So let me write this as Vn total. That's what I mean by total output noise. It's just both of the components at the same time. So this would be a sum of the output noise from example 1, which is thermal due to like thermal drain noise of M1. And for example 2, it was thermal due to thermal noise of a load resistor RL. Right? So we add them, we add the two up, and we get the total output noise. It's as simple as that. So I have subbed in the expressions for both here, and yeah, and then after a bit of rewriting and simplification, you'll get this final expression over here. So this is the total output noise due to the contribution from M1 and RL. So output noise, or let me write total output noise. Noise due to RL and M1. Right? So that's the expression. All right, so I want you to pause for a bit and look at this expression carefully. Can you recognize any familiar terms in this expression? What about this term over here, GM1RL? If you look at a common source amplifier that we have been looking in these example 1, example 2, and example 3, the gain of a common source amplifier is GM1RL in this case, right? So I can label this as gain of common source amplifier. And now look at this total output noise expression over here. This expression depends on the gain of the common source amplifier. So if I increase the gain of the amplifier, what happens to my total output noise? If I increase the gain, the output total noise also increases, right? So increase gain also increases output noise. So that's an important thing to recognize. Like if you have a higher gain, the noise is also higher. If you want to make the noise lower, then you have to make the gain lower, right? So now I want to ask yourself I want you to ask yourself a question. If I compare output noise of different circuits in, let's say, from different papers, is that a fair comparison of noise? So if the answer is not very obvious, let me ask you this, or let me ask you this through another example. Let's say I design this circuit over here, and the resistor RL, the load resistor, is variable. So let's say I tune my resistor such that the gain is very high. The maximum possible gain I can achieve by making this resistance as high as possible. And let's say I achieve a gain of 100. Okay, so excellent gain. And then I start writing a paper about this circuit that I have been developing and designing. And in the specs, I can probably write that the gain that I was able to achieve is 100. Very impressive. Now, I also have to report the output noise of my circuit, right? So being very knowledgeable about this noise equation, about this total output noise of a common source amplifier, I realized that if I can reduce the gain, I can reduce the noise. So I tune this gain lower by adjusting the value of RL to the lowest possible gain. Let's say a gain of 1, just a buffer. Okay. So, and then at this gain, I get very, very low noise. Okay. And then I report that probably on my paper that I was also able to measure very, very low noise, very, very low output noise. So is this okay? Do you see a problem with that? Well, anybody who's going to read this paper will see, wow, a gain of 100, a very high gain, and very low noise. This is excellent, right? But this is a bit misleading because, I mean, my circuit is operating in 2 different modes. Like, let me draw this out so that it's a bit more clear, right? This circuit, I'm operating it in 2 different modes. One mode is high gain, high noise. When the gain is high, I'm also getting high noise, right? And then the other mode is low gain. I can tune down the gain by adjusting RL, but then and then I can demonstrate low noise, right? So the point is that I can operate in either this mode or that mode, but to somebody who's reading this paper, they might think that I'm seeing high gain and low noise at the same time. So that's misleading, right? In reality, I'm not getting high gain and low noise at the same time. I'm either getting high gain, in which case the noise is also high, or I'm getting a low gain, but the noise is also low, right? So now I want you to think about this. If you're looking at different papers, right? Usually you would look at different topologies, even for op amps, let's say, you would look at different op amp topologies and you would compare them. These op amp topologies might have different gains and different noise, and these papers might, report different types of different noise figures, right? And so how do you compare these circuits? How do you compare these topologies? Because sometimes the gain is high, the noise is also high, the gain is low, the noise might also be low. So it's like an apples to oranges comparison. So is there a way to sort of have a fair comparison of noise, no matter the gain? Like somehow we need to sort of consider all of the circuits that are published with an equal gain. If the gain is equal, then we can look at noise and say which circuit has lower noise, which circuit has higher noise. And the circuit with lower noise is better, and the circuit with higher noise is worse. But the gain has to be the same. Because if you start mucking around with the gain, then the noise comparison is sort of meaningless, right? Because you're comparing apples to oranges again. So somehow, but now the question is, like, people are publishing around the world. We can't ask everybody in the world of analog IC design to make sure that the gain is equal and then report your noise. So instead, we have another way, which is called the input referred noise, and we basically normalize the noise by the gain, so that then it becomes a fair comparison. So in reality, you wouldn't compare output noise of different circuits from reading different papers. You would compare a better way to compare circuits would be comparing the input referred noise of the circuit, and that will be something that I discuss in the next video, because it will be about input referred noise. Okay, so that is pretty much it for this video. And yeah, again, as a summary, we discussed the motivation for finding the output noise, and we discussed the procedure or the steps to find the output noise. And then we did 3 examples to see how to implement those steps and derive the expressions for output noise. So that's pretty much it for this video, and I'll see you in the next one. Cheers.